Nicolas Malus was born in Paris, France. He participated in Napoleon's expedition into Egypt and was a member of the mathematics section in the Institute Egypt. His mathematical work was almost entirely concerned with the study of light. He studied geometric systems called ray system, closely connected to Julius Plucker's line geometry. He conducted experiments to verify Christian Huygens' theories of light and rewrote the theory in analytical form. His discovery of the polarization of light by reflection was published in 1809 and his theory of double refraction of light in crystals in 1810.
Polarization of light. Because light is a transverse wave, it can vibrate in a variety of directions compared to its direction of motion. Unpolarized light. In unpolarized light, the fluctuations in the electric field occur in all directions. It's random. As you can see here, the light beam goes one way, but those various electric field fluctuations occur in many directions. This would be an example of most of the light we see, light from a light bulb or light from the sun, say. Polarized light. Because light is a transverse wave, it can be polarized. Longitudinal waves can't. In polarized light, the electric field vibrates in only one direction. As you can see here, compared to the direction of wave motion, the light is only vibrating in one particular direction. This is polarized light. Polarizers. Unpolarized or random light can be made to be polarized with the aid of a type of filter. Take our unpolarized random light here, pass it through a polarizing filter, and the result out the other side is polarized light. This polarizing filter acts like a grate or strain that allows only one direction of motion. A good analogy is a picket fence and a rope. Imagine you have a rope passing through the slot in a picket fence. You can shake or vibrate that rope in any direction. However, once it goes through the picket fence, the slots, which have a particular orientation, allow only one direction of motion to pass through. Pairs of polarizers. A pair of polarizing filters can be used to precisely adjust the intensity of a light source. With these two pairs of filters, we can arrive at just the amount of light that we would like. The end result is polarized light of a particular reduced intensity, depending upon how we orient the filters. Intensity adjusting polarizers. With the pair of polarizing filters at a 0-degree angle with each other, in other words, parallel to each other, a maximum amount of light emerges. On the contrary, with a pair of polarizing filters set at a 90-degree angle to each other, perpendicular, a minimum amount of light emerges, virtually none. So, by adjusting the angle between the direction of the two filters, between 0 and 90 degrees, the intensity of the light can be controlled. Malus's law. This law describes how the angle between a pair of polarizers affects the average intensity, or strength, of the light, just as we previously described. S bar equals S0 bar cosine squared of theta. The S0 bar is the original average intensity of light, in units of watts per square meter. The S-bar is the reduced average intensity of light in watts per square meter. And the angle theta is the angle between the two polarizing filter axes.
I've got the camera on live view, and I've got my circular polarizer on the front. If you just watch the water in the foreground as I move my polarizer around, with a lot of light, cut it all out. You can actually see into that water, so we'll cycle it back a bit. We've got all that glare from the sun. We just turn it around a bit, and we cut that all out. And the further you go around, it'll bring back in. So just play around there. Take our shot. We're using a 6-second exposure on this at f16 at ISO 200, the smallest ISO I can use. We'll bring this up. You see we've got some loss up the top in the sky, but that's not so bad. We've got a fairly even histogram. Move in here. You can see how we can see into the water. It's one of my earlier shots. There it is with all that glare. Can't see anything. So that's this week's tip on how useful a polarizer can be.
Everyone's seen waves on water. If you look at them from the side, you can see the wave action. But light waves are different in that they have a wave action that doesn't have one particular orientation. Light waves have wave action from all rotations, simultaneously. Something strange happens when light waves are reflected off of water. They become polarized, which means that only one orientation of the light wave comes off the water. Polarized sunglasses will only pass light from one orientation as well. They're designed to block the orientation of sunlight that comes off the water, so they eliminate the glare and reflections on the lake. You'll notice that if we view the sun directly with polarized sunglasses, regardless of the direction we rotate them, we don't get rid of the sunlight, since all of its other wave orientations still pass through the glasses to our eyes. Here's an example using the polarization of light. The light bulb has light coming out of it in all polarizations. We've put one polarization filter in front of it. If we add a second filter, depending on its rotation, we'll let more or less light go to the camera on the left. If we add a third filter, the process becomes more complex. By rotating the filters at various angles, we have a great deal of control over how much light reaches the camera. Notice that we need at least 2 filters. Rotating just one filter doesn't appear to do anything to the image reaching the camera. Taking this further, if we add a lot of polarizing filters and rotate them by small amounts, we can create a lot of different levels of light. This is the principle behind LCD displays. Basic pocket calculator displays work in the same way, although in this case, the segments for the numbers are either totally on or totally off. An electric field tells the liquid crystal whether to pass light by arranging the crystal so the maximum amount of light can get through, or to block it by letting the crystal elements float in any direction they like. And this is what the final numerical display looks like, displaying the number 4.
Are you bothered by glare from the sun while driving during the day? Driving towards the sun is not only distracting, it can also be extremely dangerous. Polarized lenses are designed to reduce glare from the sun. These lenses improve safety by allowing you to recognize potential hazards on the road. As you can see, the glare from the sun is virtually eliminated, allowing you to spot hazards quickly and easily. For more information, ask about polarized lenses.
You ever wonder why fishermen use polarized sunglasses? I'm going to show you a little trick. Alright, here it is without the glasses. You can see the lights inside the building a little bit. Here it is with the polarization in the wrong way. Now watch. And hopefully you can tell how much the internal lights jump out a lot more when you use the polarizer. So I screwed up the audio on this with too much wind. As I'm turning the lenses around, you can tell that the reflections on top of the water just plain disappear. This is what polarized sunglasses are all about. They let you look onto a surface where light is reflecting back up in your eye. It works out really well, especially someone like me who has crappy vision to begin with. Once you eliminate that glare, or at least cut it down some, it